Section 8.2, Rational Exponents. Well, at the end of the last section, 8.1, we looked at how if we have a root and a power in the same expression, we can take that and turn it into just a single fraction exponent. We take the power and put it in the numerator, and we take the root and put it in the denominator. 8.2, we're going to look at rational exponents, which mean exponents that are fractions, and now we're just going in the opposite order. If we have a variable or a whole number, okay, if we're taking some base to a power and that exponent is a fraction, we can rewrite it as the numerator being the power we're taking the base to, and then the denominator of that fraction is the root, the kind of root that we are taking. And we can apply it either way. We could either first apply the power, then take the root, or we could take the root first and then apply the power, and it gets us the same result either way. So our numerator in any fractional exponent is going to be the power. The denominator of a fraction exponent is going to be the type of root. So we'll see in different cases why it'll be more beneficial to do the root first, like this. In some cases, it'll be more beneficial to take the power first. So our first example, 64 to the 1/3 power, we are going to raise 64 to the first power and take the denominator 3, take a cube root of 64. So we could look at this one of two ways. Either first take 64 to the first power, which anything to the first power is just itself, and then apply the root, the cube root of 3. Or we could apply the cube root of 3 and then take that to the first power. It's really not going to make any difference. Either way, we're really just ending up in the end taking the cube root of 64. Okay. So what number times itself again, or in other words, what number cubed gets us 64? Well, that would be 4. Okay. Moving on then to the next example. We have 36 to the 3/2 power. Actually, let's move to the right. Let's do the 1/100th to the 1/2 power. Okay, let's see if we kind of remember some of those rules of exponents. When we have a fraction to a power, we have to apply that power to the numerator and the denominator. So we'd have to take 1 to the 1/2 power and 100 to the 1/2 power. So looking at this, we can do that. If we were to take 1 to the 1/2 power, we would raise 1 to the numerator is our power, 1, and then we take the denominator as the type of root. Well, a root of index 2 would be a square root. You don't really see that the root's there, but just kind of an imaginary implied 2 on the root. Okay. Same thing with our denominator of 100. We would have to take 100, raise it to the first power, but then we'd be taking the square root of that. So again, you don't see that power of 2, or sorry, that root of 2, it's just implied. I'm writing it in for this example, but from now on I never will do that. So 1 to the first power, well, anything to the first power is just itself, so we're just square rooting 1. And in the denominator, 100 to the first power would just be 100, so we're just square rooting 100. Square root of 1 is 1, since 1 squared gets us 1. And the square root of 100 is 10, since 10 squared gets us 100. So the answer there would be 1/10. Okay. So when you have a fraction exponent, if your exponent is a fraction and it's 1/2 or something like 1/3 or 1/4, something with 1 as the numerator, you really don't have to take it to that power of 1 because that doesn't change the value. You really just have to take the root of whatever's in the denominator. In this case, it was a square root because it was the denominator of 2. So in the next example, 36 to the 3/2 power. This is really where it's going to demonstrate why it will be more beneficial to do it in one order rather than the other. Okay, so 36 to the 3/2 power means we are going to take 36 and raise it to the 3rd power, and we're going to take a root of 2, or in other words, a square root. So I guess you have to determine, you could write it either way, either 36 to the third power, but then we are square rooting that, or we could take the square root of 36 first, and then raise that to the third power. Okay, either way will work. We'll get the same answer regardless, but only one of these could I do in my head, and probably I'd assume the same with you guys. I don't know what 36 to the third power is in my head. 36 times 36 times 36. And then after we get that, then we'd have to square root it. However, I can square root 36 in my head. That gives us 6. And then you just would have to take 6 to the third power. So, I mean, then even 6 to the third power, you might not do that in your head, but it makes it some of these where it'll be a little bit easier. I would take the root first to get a smaller value, and then you're taking a smaller value to a power. So 6 to the third power is going to give us 216. Okay. So next example, we have a negative. Negative 27, raising it to the 2/3 power. Well, once again, numerator tells us the power we'll take it to. Denominator of the fraction tells us what kind of root we're going to take. So again, I would take the root first and then square the result. So this is going to equal the denominator of 3 means we're taking a cube root of negative 27. And then after we take that cube root, then we're going to square what we get. So what is the cube root of negative 27? In other words, what number cubed gets us negative 27? And that's going to be a negative 3. Negative 3 cubed gives us negative 27. But then, after we get that negative 3, and after taking the root, we then have to square it. Negative 3 times negative 3 gives us a positive 9. Okay? Just got to be careful with your signs there. Alright. So then we have another negative in our the next example over here, negative 25 to the 5/2 power. So we want to apply a power of 5 and square root the value, since it's a 2 in the denominator. So a root of 2 is a square root. We could do that first. Let's apply the square root first to get a smaller number, and then we have to take that to the 5th power. So we would be doing square rooting negative 25, and then taking that to the 5th power. But here comes an issue. We cannot take a square root, or any even root for that matter, of a negative. There's no number that if you multiply by itself 2 times would give you a negative 25. Okay, so this, remember we have to say, is not a real number. In a few sections we're going to talk about what imaginary numbers are, and then we can handle stuff like this. But for now, all you need to know is that's not a real number, so that's all you have to write. Okay, and the reasoning why, remember we can't even root. We can't take an even root. Can't take an even root of a negative. Okay. If you try to do something like that on the calculator, it will give you an error screen. So that will remind you right there that it's not a real number. The next example looks like it might be the same issue, but it's actually something different. Because the power of 5/2 is attached to the 4, we handle the 5 as our power and the 2 as our root with the 4, and that negative out front is almost like subtraction, and where we have to apply it after we apply the power. So just kind of using your order of operations, we would do this as hold off on the negative. We could take, since it's a denominator of a 2, that would be a square root that we're applying on the 4. And then after we apply that root, we would take to the 5th power. Or we could take 4 to the 5th power and then square root it, but it would be easier to give you smaller numbers to take the root first. So negative square root of 4 gives us 2. So inside the parentheses we get a 2. Then we have to apply that power of 5. 2 to the 5th power gives us 32. So this gives us a negative 32 once we apply that negative at the end. Okay. So this gives us some options to play around with, but like I said, typically, you're going to want to apply the root first. So the denominator, use that for your root, apply that first, and then take it to the power of whatever was in your numerator of your fraction. Okay, so this is how we handle rational exponents when we have fractions as exponents. All right, slide this up, and let's look at some kind of reminders of how we use the exponent rules. Okay, we already looked at exponent rules earlier in the year when they were whole numbers. Now we're going to review how we used them back then, but now we're going to use them as fractions. We're just going to add in the aspects we just talked about up here on the top of the page. So when we have a negative exponent, we have to remember that negative exponent rule. Okay. Well, when we have a negative exponent, we just take the reciprocal of our base, 16, and then apply a positive exponent. So we have to write this, the reciprocal is we flip our fraction. 16 is the same thing as saying 16 over 1. So if we reciprocal that and flip it, it becomes 1 over 16. And now attached to that 16 is a positive 3/4 power. Okay? So 1 over 16 to the 3/4 power, which is going to equal 1 over, well, the denominator of 4 in our exponent is going to be the kind of root we take. So we are going to be taking a 4th root on 16. And then after we evaluate that, we have to raise this to the 3rd power, because that was the numerator of our fraction exponent. Okay. So this equals 1 over the 4th root of 16. What number to the 4th power will give us 16? 2 times 2 times 2 times 2 will do that. So 2. But then we have to take that 2 and raise it to the 3rd power. And that gives us 1 over 8. Because 2 cubed, or 2 to the 3rd power, is equal to 8. Okay. Let's look at the next one here. We have ourselves 8 over 27th. So we have a fraction raised to a negative exponent. That also happens to be a fraction. So this could be a little tricky. Let's remind ourselves, remember how to handle this. Again, a negative exponent, remember that means you just take the whatever base you have and take its reciprocal. So we already have a fraction here. So we have to take this fraction and flip it. And then we can make that a positive 2/3 exponent. So this is going to be equivalent to 27 over 8. And now we can write this as being to the positive 2/3 power. Okay, we don't change the exponent. We don't flip the exponent fraction. Just the base that we're taking to that exponent. That's the fraction we flip. Okay, hopefully you can read that. So now we have to apply that 2/3 power to the numerator and the denominator, the 27 and the 8. So on both the top and bottom here, we will be taking a cube root, a root of 3, and then taking that to a power of 2. So we'll be cube rooting 27. And then squaring that result. And then we will be cube rooting 8 and squaring that result. Okay. Because that's what a fraction exponent would tell us to do, like 2/3 would tell us to do. The cube root of 27, what number cubed gives us 27? That would be 3. So in the numerator we have to square the 3. And then in the denominator, the cube root of 8 would give us 2, since 2 cubed gives you 8. And so we have to square the 2. So doing so, 3 squared gives you 9. 2 squared gives us 4. So we get the fraction 9/4. So that gives us that kind of that process, just bringing back these rules of exponents. All right. The homework then gets into some of these examples, kind of tricky examples that look even more difficult. The next example we have here is 6x to the 2/3 minus 4x to the 3/5. Okay, you're going to see something like this in the homework. Well, the power, unless there's a parenthesis around the whole expression, then the exponent is really just being applied to the variable that it's attached to. So in that first term, the 6x to the 2/3, the 2/3 power is only being applied to the x, not the 6. So we can rewrite this as equals 6, that's not affected, but then x being taken to the 2/3 power would be a cube root of x, since the denominator of that power was 3, and then after we did that, we would square that expression. And then minus, now the 4x is in parentheses, so in this expression we would have to take the 3/5 power to everything. So in this one we would take a 5th root, since 5 was in the denominator, but we take the 5th root of the whole expression 4x, and after that then we would raise that to the 3rd power. Okay, and there's really nothing we can do here with this because we can't cube root x, we don't know what that x value is. We can't 5th root 4x because, well, we don't know what that x value is. You could write it that way, although you could have wrote this an alternative way. Let's see here. Or if you would have taken the power first and then applied the exponent, so here taken x to the 2 power and then cube rooted it, and then taken 4x to the 3rd power and then 5th rooted it. So how that would look would be 6, and then if we had taken x and squared it first and then cube rooted it, minus taking the 4x and cubing it first and then 5th rooting that. So this is just what it said at the top of the page of the notes. You could either apply the roots first and then take it to the power, which is in the numerator of your fractions, or you could apply the roots secondly, do the powers first underneath the radical symbols and then apply your roots after it. Okay, so either of these two expressions would be correct. Alright, well, what if you have two terms, like in our next example, a squared plus b squared, both inside of the same parenthesis being raised to the 1/2 power? That means this power of 1/2 needs to be applied to the entire expression. So how we show that it's being applied to the entire expression is we take the root to the entire expression and take the power to the entire expression. But remember up top what happened when we raised something to a fraction exponent where 1 was in the numerator? If we raise anything to the power of 1, it doesn't change the value. So we really don't even have to worry about raising to an exponent, raising to a power when we have 1 in the numerator. We can just keep the expression as it is, a squared plus b squared. But because we have that denominator in our exponent, the denominator of that fraction is 2, that would be a square root we have to take. And because the whole expression is in parentheses, the square root has to go over everything. That power, that 1/2, okay, that square root is being applied to everything. So it'd be a squared plus b squared all over a square root, and a radical symbol. Okay. All right. And now just a little more what we learned at the end of last section. Okay, so hopefully this should be easy. Now let's go in the opposite direction. If we have a fourth root and we're taking 3 to the 8th power, rather than actually taking 3 to the 8th power, because that's again probably something you can't do in your head, let's just work backward from what we just learned today, what we just learned now. This is equivalent to taking 3 to the, well, the power we could write as the numerator of our exponent over the denominator is going to be whatever the root was, in this case a root of 4. So this is like taking 3 and raising it to the 8/4 power. Well, 8 divided by 4 equals 2. So this is equivalent to saying 3 squared. And 3 squared gives us 9. Okay. So that's something you could do in your head if you remember the rules, whereas you probably can't take 3 to the 8th power in your head. I don't know what 3 times 3 times 3 times 3 8 times equals. Assuming you probably don't either. Okay, using the same rule on the next example, the 6th root of z to the 6. Well, first of all, you can kind of remember that the powers and a 6th power and a 6th root will cancel each other out. Or you can think of it as this fraction idea. We can make our exponent as a fraction. 6 will be our numerator since we are raising to the 6th power. 6 will also be our denominator since we're taking a 6th root. But 6 over 6, we could reduce that fraction. That equals 1. And, well, anything to the first power is really just itself. Z to the first power just means z. So that whole expression would then simplify to just being a z. Okay? And in this section, technically, because this is being taken to an even power, the result would definitely have to be even. So whatever number we started with here for z, we'd get back to that value, except if it was negative to begin with, it would have to be positive. But I don't think in this section they make you do the whole absolute value around the z. I believe only in that 8.1 do they worry about those. Okay? Because in this whole section, I think it's assumed that all of our variables are positive numbers. I believe that's what we're assuming in this section. Okay? So like I said, I don't believe we need to put the absolute value around there. Alright, we can now look at the second page of these notes. And we have a little bit more applying the exponent rules. Okay, some even trickier examples. So for our first example, we have 2.5, or 2 to the 1/2 power, times 2 to the 1/2 power again. Well, this is an expression where we're multiplying, we're taking a product that has the same bases. We can apply the product rule. Remember, the product rule told us that we can, if we have the same base, which we do in this case, both are base 2, and we're multiplying them, then we add the exponents. Okay? So maybe put a little note of that. This is a product rule situation. That is where we add the exponents. Okay? So this equals 2 to the 1/2 plus 1/4 power. Okay? And I'm not going to review here how to add fractions. I assume we either can at this point or can do that on the calculator. And 1/2 plus 1/4 gives us 3/4. So this is equivalent to saying 2 to the 3/4 power. And we could then take that expression and write it as the fourth root of 2 to the third power, or we could write that as the fourth root of 2, all raised in parentheses, raised to the third power. But in this section, in these questions, I think it's just going to ask you to keep it as a fractional exponent form. So just got to be careful, read the directions on the My Math Lab homework. It'll say when it wants it as a radical, and then it will say when it wants it just as a rational exponent, which that's what this is, a rational exponent. It's a fraction. Okay? So that's exponential form. Next example, we are dividing two things. In other words, we're taking a quotient, and again, they have the same base. Both of them are base 5. Here the rule, we call this the quotient rule, and the rule was that we subtract the exponents. Okay, we subtract the exponents. So this is going to equal, we keep that base 5, and we have to take 2/3 and subtract from it 7/3. So that will give us our new exponent once we do that subtraction. 2/3 minus 7/3. Okay, subtracting there gives us 2/3 minus 7/3 gives us a negative 5/3. So we have 5 to the negative 5/3. Which would be great if we were allowed to keep keep exponents as negatives, but if you recall from those exponent sections, that's never going to be the case. So we now have to apply that negative exponent rule, which just means we take what we have, our base, and we have to take its reciprocal. So 5 you can think of as 5/1. We have to take the reciprocal, so we have to flip and make it 1/5. Okay, so applying the negative exponent rule. In order to write that as a positive exponent, we have to take the reciprocal, so 1/5. And now that we've taken the reciprocal, now we can write it as a positive exponent. So 1/5 to the positive 5/3 power. Okay? It's getting tough to squeeze that in there, but so 1/5 to the 5/3 power. Negative exponent rule. Okay. Alright, we have a couple more here. The next one is one of those that we really seem to hate back when we did them earlier in the year, and now we're having to do it with fraction exponents, which makes it really tricky. We have x to the 4th, y to the negative 6, over x to the negative 2, y to the 1/3. So right off the bat, we can use the negative exponent rule inside the parentheses to move those pieces around that have negative exponents attached to them. Okay, so go ahead and do that. The x to the negative 2, we can bring that up top and make it a positive 2. Y to the negative 6, we can bring that down below, make that a positive 6. So again, we'll start by using the negative exponent rule. Okay, so that is going to equal x to the 4th stays up top. Then we're bringing up an x to the negative 2, so we'll end up having an x to the positive 2. That's not showing up very well. X to the positive 2 times the x to the positive 4 that was already there, over, we already had a y to the 1/3, And now we're going to bring down a y to the 6. Well, no, y to the negative 6, but we make it positive now that we moved it. Okay? And everything is outside the parentheses is being raised to the negative 2/3 power. Alright, so from here we can then use the product rule. Bring this back up here. Product rule where we add the exponents. So x squared times x to the 4th gives us x to the 6 over y to the 1/3 times y to the 6. Well, if we add 6 plus 1/3, it ends up giving us 19/3. Okay. And still we have not done anything with that negative 2/3 exponent on the outside. So again, to get here, we use the product rule. And maybe if you want to leave yourself a little note, if we did 6 plus 1/3, we'd have to convert 6 to a fraction with 3 in the bottom. That's equivalent to saying 18/3. So 18/3 plus the 1/3 gives us 19/3. Okay. So that's how we get there. Now that we've simplified inside our parenthesis, now we can apply the negative exponent rule to make it become a positive 2/3 exponent on the outside. To do that, we have to flip our fraction. So this is going to equal, we bring the y to the 19/3 up top over x to the 6 down below, and now we can make it a positive 2/3 exponent. So again, we use the negative exponent rule. Alright, finally getting here now. And lastly, we have to apply that power of 2/3 to both the numerator and the denominator. We're using the power rule, where we do a power to a power. If you remember the rule there, when you do the power rule, you multiply your exponents. So this is equivalent to saying y to the 19/3 power times 2/3 over, we had x to the 6, but we have to multiply that 6 times 2/3 as well. So we have to apply that power of 2/3 to every single factor in both the numerator and the denominator. Alright, so now just multiplying, we'll have our final answer. And that gives us, well, 19/3 times 2/3 gives us 38/3. You can multiply fractions straight across. Over 6 times 2/3 gives you 12/3, which is 4 over x to the 4th. Okay. And again, to get from here to here, we had to use the power rule. Alright, and that would be our final answer. Y to the 38/3, or sorry, 38/9. I wrote that wrong. Y to the 38/9 over x to the 4th. Because remember, multiplying 19 times 2 would give you 38. 3 times 3 would give you 9. Multiplying fractions, you actually multiply across. Adding fractions, you would have kept the common denominator. Not there. Alright, last example. We have m to the 3/4 out in front of a parenthesis, m to the 5/4 minus m to the 1/4. So what we would need to do, just like any time we have something out in front of a parenthesis, we need to multiply it by everything inside. We call that, of course, distributing. So, breaking this down, this is going to be equivalent to saying m to the 3/4 power times m
to the 5/4 power minus m to the 3/4 power times m to the 1/4 power. Okay, so that's actually writing the two products out, the two multiplications we're doing out. What rule are we using? Since we have all the same base m and we're multiplying, we're taking a product, so we got to use the product rule. Okay. Product rule, multiplying things with the same base m here, we add the exponents. So this equals m to the 3/4 plus 5/4 minus m to the 3/4 plus 1/4. Okay, that's what the product rule tells us we can do. And that's 3/4 plus 5/4. And then 3/4 plus 1/4. So let's go through and add our exponents. 3/4 plus 5/4 gives us 8/4 minus 3/4 plus 1/4 gives us 4/4. Remember, when we add exponents, or when we add fractions, we keep the common denominator, just add across the numerators. Okay, so that's why both of these fractions still have a 4 in the denominator. And well, we can reduce those fractional exponents now. 8 divided by 4 gives us 2, minus 4 divided by 4 is 1. So m to the 1 power, m to the first power, is the same thing as just saying m. So there would be our final answer. You don't need to try to factor it back or anything. M squared minus m won't combine because those aren't like terms. So we just keep it how it is. And that is all of section 8.2.